the US grid is going to be capped by 2030. We will be out of power in the United States by 2031. Europe will be out first. So something has to give. We have to become more efficient with the way we utilize these resources, the algorithms we build.
Hello, and welcome to Environment Variables, brought to you by the Green Software Foundation. In each episode, we discuss the latest news and events surrounding green software. On our show, you can expect candid conversations with top experts in their field who have a passion for how to reduce the greenhouse gas emissions of software. I'm your host, Chris Adams.
Hello and welcome to This Week in Software, where we bring you the latest news and insights from the world of sustainable software. This week, I'm your guest host, Anne Currie. As you know, I'm quite often your guest host, so you're not hearing the dulcet tones of the usual host, Chris Adams. Today, we'll be talking to Chris Liljenstolpe, Christopher Liljenstolpe, and a leading expert in data center architecture and sustainability at Cisco Networks. Christopher is also the father of Project Calico and co-founder of TWiGS, and he's a super expert in cloud infrastructure and green computing. But before I introduce him, I'm going to make it clear. I've known Chris for years because he's worked very closely with my husband. So we know each other very well. So that might explain why we seem like we know each other quite well. Who knows? What I do know from Chris is that it's impossible to say what we'll be talking about today. We will go all over the place. But Chris, do you want to introduce?
We might even cover the topic at hand, although that is an unlikely outcome, but who knows? That might be a first. That would be a first, but it might be an outcome.
So introduce yourself.
Sure. So as Anne said, my name is Christopher Liljenstolpe. I'm currently the Senior Director for Data Center Architecture and Sustainability here at Cisco, which means, once again, I failed to duck. So I'm the poor sod who's gotten the job of trying to square an interesting circle, which is how do we build sustainable data centers? What does a sustainable data center look like? At the same time, dealing with this oncoming light at the end of the tunnel that is certainly not sunshine and bluebirds, but is a locomotive called AI, and it's bringing with it gigawatt data centers. So, put that in perspective. Intel 2 years ago, we were talking about a high-power data center might be a 90 kilowatt rack data center, or a 100 kilowatt rack data center, or a 60 kilowatt rack data center. And about 2 years ago, we went to, it might be 150 kilowatt rack data center, and that was up from 30 kilowatts from years ago. Took a very long time to get to 30 kilowatts. That was good from 2 years ago to 9 months ago. 9 months ago, went from 150 kilowatts to 250 kilowatts. So it took us decades to get from 2 kilowatts to 90 kilowatts to 150 kilowatts. And then in a year, we went from 150 to 250, maybe 350. Jensen last week just took us to 600 kilowatts a rack. So yeah, that light at the end of the tunnel is not sunshine at the end of the tunnel. So yeah, how do we do sustainable data centers when you've got racks that need nuclear power plants that need strapped into each and every rack? So yeah, I'm the one who gets to figure out, what does a gigawatt data center look like and how do you make it sustainable? So that's my day job. And this really becomes a system of systems problem, which is usually what I end up doing throughout most of my career. Put the Lego blocks together, build system of systems, and then figure out what Lego blocks are missing and what we need to build. So I did that with Anne's husband on a slightly different space, which was how do you build very scalable networks with millions of endpoints for Kubernetes. And now I'm doing this for data center infrastructure.
Which at least is absolutely fascinating. So for listeners, a bit of background on me. I'm one of the authors of O'Reilly's new book, Building Green Software. I'm also the CEO of learning and development company Strategically Green with the husband who used to work with Chris. In building green software, Chris was a major contributor to the networking chapter. So if you're interested in some of the background in this, the networking chapter is very high level. You don't need to know any super amazing stuff about it. It'll ramp you up on the basics of networking. So have a read of that if you want a kind of a little bit of a lightweight background to what we're talking about today. But actually, what we're talking about today is not networking. Is obviously a key part of any data center, but that's not really where your focus is on the moment. It sounds like more like energy is what you're caring about at the moment with DCs. Is that true, or both? It'll always be both.
It's both. The energy starts behaving a bit like networking, a bit at this level. And it's getting the energy in and getting the energy out as well. The cooling is actually a real interesting part of it. But we really start thinking about the energy as an energy network. We almost have to when we start thinking about energy flows this size and controlling them and managing them. And then there's other aspects to this as well. Some of the things that are driving this insane, I'll be right out and say it, this insane per rack density. Why do we need 600 kilowatt racks? Do we need 600 kilowatt racks? But let's assume we do need them. Why do we need them? We need to pack as many GPUs as closely together as possible. And that means that and why do we need to do that? We need to get them as close together as possible because we want them to be network close for very, very high speed so that we have a very high performance cluster or closely bound cluster so that you get your chat GPT answers very quickly and they don't hallucinate. So that means putting lots of GPUs and a very high bandwidth memory very close to one another. And when you do that in networking, you want that to be in copper. You want that to be a very specific kind of networking that really ends up using a whole lot of energy unless you pack it very, very closely together. So that 600 kilowatts is actually the low power variant. If we stretch further out, it would be by another order of magnitude because we'd have to go into fiber. So we pack it very close. And that means we end up packing a lot of stuff very closely together. That drives a lot of power into one rack, and it takes a lot of power to get the heat back out of it again. So it would be worse if we stretched it further out, but it's partially a networking thing that's driving this actually. So is there one of the levers we can try and pull? Is there a better way of doing this networking to cluster these things tighter together? So it always comes back to the network, one way or the other.
It does indeed always come. So, although I live in a networking household, I'm not so familiar with it. I don't know how this works. Is this that the GPUs have to talk together very fast, so there's almost no elapsed transit time in messages between the machines? Is that why the GPUs
that you want to get as many GPUs talking as closely together as possible, more specifically GPUs and their high bandwidth memory. So the HBM stacks, the high bandwidth memory stacks, and the GPUs. The minute that you have the way, and one could question if this is a good architecture or not. There are basically in a AI infrastructure, there's 3 networks that tie the infrastructure together. There's what's called the scale-up network, which is the very, very high-speed network that stitches some number of GPUs together. And that's on the order of today, anywhere from 3.6 terabits per second upwards to what's coming down the road about 10 terabits a second, what's called non-blocking traffic network between the GPUs in a scale-up cluster. And that could be anywhere from 8 GPUs up to now, within the next year or two, 500 and some odd GPUs in that cluster. So in that realm, you could have up to 500 GPUs all talking to each other at 10 terabits a second or 8 terabits a second, depending on the GPU manufacturer, et cetera. And that's the highest performing part of the network. And then those clusters are talking to other GPUs in other clusters at usually around 800 gigabits a second. So that's a huge step down in performance. And then those GPUs are talking to the outside world. All those GPUs are into the outside world at the servers those things are in. And usually those are packaged for 8 GPUs in the server. Those servers talking to the outside world at 800 gigabits a second per server. And that's how they get their data. That's how they get their requests and how they give their answers. So 800 gigabits.
I'm going to stop. I'm going to stop now and ask a stupid question, which is a very simple question. So stepping back, a network, and I'm not a network expert, so I might be about to say something totally stupid here. So networks, there are at least two very important things about networks. One is the bandwidth. The bandwidth is how much data can you get down the pipes from one place to another. And the other is latency. How long does it take to do it? So I think what you're saying there, if I understand it correctly, is AI really, really needs high bandwidth, and that's what's driving it. It doesn't latency. It's not latency. It's bandwidth. Or am I wrong?
You are correct, and people get that wrong. Because there's such high bandwidth, the latency doesn't matter as much. Head-end latency, because the amount of data being moved is big and the bandwidth is high. There is a little bit of a latency hit, but high performance computing is more latency sensitive. If you've got a very high bandwidth network, the data packets are actually pretty small. So the latency isn't as big a hit. The third is congestion. Congestion kills an AI network. And this is the problem. So if I can take the whole model that I'm computing against and put it in that scale up domain, then everything can talk to everything at full bandwidth and there's no congestion. But if you remember, those GPUs that are in the high bandwidth domain, there's 8 today, or maybe 72, or 36, or 256, or maybe 500 and some odd if Jensen's build is correct, and some of the other things working on with some other vendors might be correct. So that's a lot of bandwidth. But if you can't fit it all in that one, then they have to go over that slower 800 gig per GPU versus 10 terabits per GPU to talk to a GPU in another one of those high bandwidth clusters. And all of a sudden you go from 10 terabits or 8 terabits or 3 terabits even to 800 gigabits. So that's all of a sudden a much more contended or congested network. So you go from running down a motorway at 2 o'clock in the morning to a B side road with lots of people on it, and the GPUs do this.
Oh, yeah.
And everything slows to a crawl. And all the GPUs go to massive, basically idle. And that's what people don't want, because those GPUs are very expensive. Those GPU servers are hundreds of thousands of dollars. They use a lot of power, and they're just idling, waiting for the GPU on the other side of that slow link to get back with an answer. So you don't want your model or that you're inferring against or your training to be split across these things. So you want everything on that high-speed link. And if you want everything on that very high-speed link, that multiple terabits per second per GPU, and to think about this, that means that if I've got 8 GPUs in a server, that means I've got 80 terabits of bandwidth coming into that server. And if I've got 10 servers, let's say, in that cluster, that means I've got 80 terabits of bandwidth between that server and every other server in that cluster. And when you do the math, that's about 10,000 cables running up and down inside that rack. So the cabling becomes interesting. There's all sorts of interesting problems here. So I cram everything in. So this is why I want to get everything crammed in as tightly as possible. So I can get as many things into that rack. It's an easier problem. And the power to put that on copper that runs maybe 1 meter in length or 1.5 meters is less than a watt per cable, per what's called SerDes. Put it on fiber, I'm over a watt, at least maybe over a couple of watts. So I go from 1/10 of a watt to a couple of watts. And it takes more space on the board and everything else. So that we get into physics problems. So that's why I need to pack it in tight. That's why I need more power in a higher density space, because I want to get everything into that one high bandwidth domain. Now, another practice might be to do away with this concept of scale out and scale up. And there's some architectures that might do that, but the main model today, the NVIDIA model, is scale up and scale out are kept separate. One can argue, is that a good model? It is the model in the industry today. That means the software developers have to be cogent of that as well. And the scheduler, people who design the schedulers, have to be cogent of that as well. And so this is a design that now ripples through the entire architecture all the way through up through the software stack and everything else.
So what you're saying is that when we talk about AI and we talk about GPUs and all that kind of stuff and the incredible amount of power that it requires, we tend not to think about the fact that actually it's the networking that requires one hell of a lot of that power. This is not networking going, across the country. This is not networking outside the data centers. This is networking inside the data centers.
This is networking in the rack. This is a 1 meter diameter or 2 meter diameter network. And it's tens of thousands of cables.
So I'm sure that something you've been thinking about a lot recently is the enormous shift that's taken place with DeepSeek coming in.
Yes.
Has that completely? Have you got? How much of an effect does that have on the network side of things?
So the whole idea behind DeepSeek is you don't need to do, from a training perspective, I think of it as the data is sort of pre-trained. So you don't need to do as much pre-training. You don't need to do as much training. Therefore, you don't need as many GPUs to sort of prep your data, prep your model. So that means you don't need as big a scale up cluster to train, to get ready, to infer. And remember, training doesn't make you any money. If you're in this to make money, training doesn't make you any money. It's inference. It's using the models what makes the money. And potentially inference as well might be impacted. But Jensen made an interesting point, was as we start doing reasoned inference, that's going to require a lot more compute. Now it starts looking more like inference, like training. And you're going to make, up till recently, inference was always one and done. You make one pass through inference and you get the result. And that's why we used to get some interesting, let's just call them interesting results. We used to call it, hallucinations. But now you take and you make one pass through and then you sort of check it. Does it make sense? And do you reason? Does it look reasonable? And you make another pass through again and another pass through again and pass through again. This reasoned inference. That all of a sudden starts using a lot more compute, looks a little bit more like a training job almost. And that now starts using a lot more GPUs, and you need more scale up bandwidth and GPUs. So it'll be interesting to see if DeepSeek should benefit that reasoned inference as well. The bigger question is, DeepSeek will probably only be as good as the pre-trained data they ingest, right? So this sort of becomes, do we feed our AIs with other AI data? And at some point, do we all become self-referenced, right? Do we take AI data to feed other AI data? And pretty soon we're all, it's like, if all the code in GitHub is written by AIs, and then we train coding models for GitHub using Git AI written code, is that a good thing or not a good thing?
Well, I guess it depends who's tested code. I mean, if they also write tests and they run the tests and the code works, then, but.
Yeah. Yeah, of course. It's sort of like having the developer write their code too, right? You end up with a monoculture.
Yeah, that is
right?
true. Yeah.
You end up with a monoculture.
Yeah.
Or not. Maybe you don't end up with monoculture. I don't know. This is, now we're getting into philosophy.
So it's interesting. I do know.
And now, does everyone just watch this went from infrastructure to software design philosophy? Long.
It's, the AI stuff I do find quite fascinating. I do know somebody who's a DeepMind engineer and used to work on OpenAI. And I remember them telling me years and years ago, that the massive change, the switch from, it was kind of when AI was starting to get good. I was talking to him nearly 10 years ago. I was like, suddenly it's got a lot better. Why has it got a lot better? And he said, it's randomness. We realized that actually if you injected a load of randomness into, his decision making, suddenly it got vastly better. It was a sea change. So it's not as predictable, and it's odd that AI, something we don't talk about a lot, is that AI is based at its heart on the injection of randomness, which I find fascinating. And then
there was an interesting study. If you train AI on bad data in one domain, it will start giving you bad results off of other domains as
really
well.
That's interesting.
Which was a really sort of but anyway, now we're really off the rails.
Yeah, we are. And in fact, we've only got 10 minutes left, so we should actually go back onto sustainability, because the question I wanted to ask you mentioned in our bit that we were talking about there about racks, that racks are becoming, you need a nuclear power station for every rack these days. But is that literally the case? Can this only be done through nuclear, or can it be done like Texas are making calls for large flexible loads for all their mega amounts of solar that they're running here? Is it realistic? What do you think? Is nuclear and AI is it a prerequisite?
It's not a prerequisite, but it is probably going to be a baseload kind of demand. And that's because the amount, at least at this point, the amount of money you will invest, if you're going to put up anything 100 megawatts or more of AI compute, that is a serious amount of investment. Let's also be honest. If you're talking about 500 megawatts or a gigawatt facility, you're not lifting a substation permit, because there aren't substations for things like that. You are going to jack yourself into a power plant, because at that point, a gigawatt is a power generation station, right? That is a reactor in a nuclear power station. That is a gas generator, a gas turbine in a cogeneration power plant, etc. It's a turbine in a major hydro, right? It is a full-scale commercial power plant unit. So there's no reason to have a substation, because you are consuming a full commercial power plant. So you might as well planted there. And that's not small money. You're going to have to guarantee a load to a power company to do that. One. Two, the amount you're going to spend on the GPUs, let alone all the other infrastructure that goes around it, that is a huge capital investment. You are not going to want that sitting idle for 1 minute in a year. So that is going to be a base load that will always, and your shareholders are going to string you up. That will always be running. So that's going to be a base load. So something's going to have to support that base load. It could be solar, but then you're going to have a very big battery plant. There's one going in India. There's a 1 gigawatt facility going in for AI when it's fully built out, and it's going to be held up by a solar plant. That solar plant is going to be 1/3 of the ground is going to be solar, and the remainder is going to be battery to hold the thing for 24/7. So they will be doing solar, but it's going to be solar battery. But yeah, this will be, you're going to want this thing running all the time. So we joke about it being nuclear. The funny thing was, 3 years ago, we were saying these small modular reactors, 100 megawatts, that's a perfect size for a data hall. Now we're just saying, go, unshutter your commercial nuclear reactors, because the gigawatt size commercial nuclear reactors are now about the right size. The interesting part to that is, what do you do when you have to refuel the reactor? Because the reactors, most commercial reactors, have to be shut down when you refuel. If you're jacked into a reactor, what do you do when they have to shut down the reactor? That's a year process. What do you do for power? Because you're probably not connected to the grid. You're connected to, like what they did in Pennsylvania. You're connected to the reactor. What do you do for power when they shut down that reactor? I hope the folks have thought about that. Maybe you still do small modulars. Maybe you do 12 small modulars at 100 megawatts each, and you sort of have an N+2. Interesting thoughts.
That is a very interesting thought. So so you're making two fascinating points there that I have never heard made. One is that we've totally run ahead of SMRs, all that thing. We've galloped ahead of that. And yet it might actually be worth bringing them back, just because of their kind of modern resilience thing of, it's better to have 10 than one. Better to have 10 small ones than one big one.
Yeah, I've got resilient reactors. And if it's the molten salts, you can refuel them by just topping off the salt tanks as you go. And you can remove the poison out of them as you go. So, just back the salt truck up and dump more salt in. It's a little more than that. It's sort of that. Yeah. If you're interested in bashing your head into the wall and learning about things that you never thought you'd have to learn about, this is a fun time to get into data center infrastructure, because you get to do things like, okay, how do I cram a couple hundred terabits per second into a network in a rack, at the same time talk about liquid molten salt reactors? It's sort of a broad spectrum of, let's also talk about signal integrity of dielectric fluids, because we might have to send all of the stuff swimming in a tank. It's you have a lot of interesting conversations in one day.
It sounds like you're in a pretty fun area at the moment. And we thought it was fun. We thought cloud networking was fun 5 years ago. There's nothing, as it turns out.
Yeah. So, and the one thing that's sort of interesting now is we took Scalable Sustainable Infrastructure Alliance and the Linux Foundation. We merged it, as I'm sure you've heard, with Green Software Foundation, so we thought it was probably time to get the hardware guys and the software guys gals talking together, because we realized that we really needed to have the stack not have this wall between the hardware and the software. We really needed to have the same things we were talking about before I alluded to. It's like, okay, the hardware impacts of the horror show that we've got going on. I say that in the nicest possible way to my friends doing the chips. This unique challenges that we have coming, we really need better understanding on the scheduler sides, et cetera, and how we manage that, monitor that, and the impacts of that on the software side. So we decided to take the folks who are working on open hardware designs and making those sustainable and marrying that to the software side, and the green software folks who are working on how we manage and monitor that as well. So we decided to take those two and put them together. And the first project out of that is going to be something called Project Mycelium, which is going to be actually looking at how we build software linkages on how you manage and monitor the hardware infrastructure on the software side.
Named after the networks of funguses under the way that actually everything in a forest is more connected together than we'd ever realized previously, using these incredible mycelium collections. I take it. I'm guessing that's why it's named that way.
Exactly. Exactly. And a good friend of mine, Mai Trong, who used to be the CTO, field CTO at Equinix, is going to be running that project for me there.
So yeah, utterly fascinating stuff. So yes, I mean, so stepping back from all of this, it's mind-blowing amount of complex new thoughts and approaches to things. And what's your view? I mean, you have a kind of 30,000, 40,000 foot view, tend to on all of these things. What are you thinking? Where's it all going? What's going to happen?
Well, one of my jokes is, yes, AI will kill us all. The question is, will it get smart enough and realize we're the problem and actively kill us? Or will it just take so much resources, it will just melt all the ice caps and create a water world before it becomes sentient and just kill us that way? That's it. There's a joke in every joke. I think right now, the path that we're on, frankly, is not sustainable. We can't, the next logical step from this is we're looking, if we follow that train of 150, 60, 100, 150, 250, 600, it's north of a megawatt rack. That path is unsustainable, both from resources, power, but also economics. We can't do that. At the going rate, the U.S. grid is going to be capped by 2031. We will be out of power in the United States by 2031. Europe will be out first. So something has to give. We have to become more efficient with the way we utilize these resources, the algorithms we build. We're still brute forcing AI. We think this is all brilliant software. It's not. We're still brute forcing the heck out of this stuff. So something's got to give there. I think when that does, there'll be a lot of business models that might face some challenges, because there's a lot of value built that this is going to continue going this way. But it needs to happen. So we're going to end up, I think, and there's a lot of fluff as well. There's a lot of the equivalent of pets.com out there right now. I think we'll end up with a lot more distributed use cases for AI that don't need the same amount of power. We don't need huge inference across it. But the current trend will have to get adjusted, and somebody's going to figure it out.
The old
Many people
quote,
will figure it out.
if something can't go on, it won't. It'll
Right.
stop. it's
there will be enough economic pressure that it will drive an innovation that will fix it. So I just looking at it, just
it's the code.
I'm not sure how we'll mine enough copper to support this building the power transmission infrastructure. So anyway, that's my doom and gloom part of this. But I think it's what we will end up by the time we're done with it, though, is a very efficient computational infrastructure. Because it's forcing us to look at everything along the stack. Air is an absolutely horrible heat transfer fluid. Everyone's running madly down the road of liquid. Everyone's running madly down the road of higher voltage, which again, the way we transmit power in a data center is pretty horrible today. Everyone's bringing all the efficiencies they can out of that because now we have to. It's just economically impossible to do it any other way. So whatever comes out of the back of this is we're going to have a very efficient data center infrastructure, which is all for the better. We're probably going to end up we will probably end up driving. This will probably fix the grids because it has to, because we're driving a very different power transmission infrastructure. So we'll fix a bunch of problems along the way. Man, silver lining.
And there is a lot of money behind it. So it is actually aligned with a lot of good things that we want, and it's driving a lot of money in those directions. Yeah, it's interesting if it doesn't kill us all, which
And who knows? It will probably bring back nuclear. We'll probably be able to have rational conversations about other non-carbon emitting power sources that
space-based solar power. Well, I'm desperate for it.
Maybe. Might get some countries that just recently shuttered all their nuclear plants go back and put their cooling towers back up. I'm not talking about any European countries.
Well, I'm sure everybody's brain is completely full now. So and we've had a really, really interesting discussion that I have utterly enjoyed. So I think we should probably draw the podcast to an end with any final comments that anybody wants to make. So everything we talked about that we can put in the show notes will be in the show notes at the bottom of the episode. Do you have any final points that you want to make now?
I mean, it is fun times. And it's not all doom and gloom, but it is right now. There is a bit of a hype, and it at this point it seems like it is a train that's going to keep on going, and it will correct. But it is leading to a lot of innovation, and that innovation will hang around. Just like when the .com bust happened, we will see a correction here. And what people thought originally the internet was going to do and what was going to be delivered by the internet didn't really happen. But it's certainly the things that it is used for. The people who originally created the ARPANET, or the people who invested in the .com original late 90s explosion, the money they put into it, they did not foresee what it is being used for now. But the world has been, forever changed by that, for good and ill, both, by that investment. And it's going to be the same thing here. What we're investing in building now, we think we know what it's going to be used for. We're wrong. Everything we think it's going to be used for, 5% of it will probably be still what it's being used for 15 years from now. The rest of it, we have no idea. And we'll benefit from it and we'll suffer for it. But we're building a base infrastructure, and other people will actually build on that base infrastructure and deliver things that we will have no idea about.
Yeah, that reminds me of sort of a discussion that we had a few years back about why the internet survived 2020, the beginning of the pandemic, which kept up the West, because otherwise if we hadn't been able to all stay at home and work over video conferencing, things like that. And a lot of the infrastructure that was put in place that we relied on there was to support high definition stream TV. So it was like people put it in so the folk could watch Game of Thrones. Then Game of Thrones saved the West. It's like who would have predicted that? You just don't know what's going to happen.
Exactly. Yep. Indeed. And that infrastructure, actually, which we didn't talk about, was put in place because service providers made a horrible choice early on of putting in broadband that was the cheap choice that couldn't do multicast. If they had put in multicast capable infrastructure, they wouldn't have put in the amount of backbone infrastructure that they did, because they would have had multicast and they wouldn't have had to do the build that they did, which indeed actually helped us. So it was, the not having multicast out there actually probably saved our bacon. And that pains me to no end. Because I was sitting there banging away in the mid 90s, etc. It's like, we need to get multicast out there. It's so much more efficient. It will save so much money. And if we had, we probably would have been in much worse shape when the pandemic hit.
It is interesting that flabbiness, things like inefficient code, and inefficient code is what we've been building for the past 20 years. Most of my career, we've been building highly inefficient code, but it does mean there's a lot of untapped potential in there to improve. It's unrealized potential as a result of lazy behavior in the past. We're mining our own past laziness. That might save us all. But on that note, our laziness and lack of foresight in the past have tended to save us in the future, might well save us again. On that happy note, or that nuanced note, thank you very much for listening, and thank you very much for being my excellent guest today, Chris.
Thank you for having me on, and thank you everyone for listening. I hope it was, if not educational, at least entertaining.
I'm sure it was both. Thank you very much, and speak to you all the next time I'm hosting the Environment Variables podcast. Goodbye.
Bye, everyone.
Hey everyone, thanks for listening. Just a reminder to follow Environment Variables on Apple Podcasts, Spotify, or wherever you get your podcasts. And please do leave a rating and review if you like what we're doing. It helps other people discover the show. And of course, we'd love to have more listeners. To find out more about the Green Software Foundation, please visit greensoftware.foundation. That's greensoftware.foundation in any browser. Thanks again, and see you in the next episode.